Hello guys, my name is Manojit Das and I am one of the TA in this course NPTEL Mechanisms in Organic Chemistry taken by Nandita Madhavan ma'am. So before I start, I would like to briefly introduce myself, not only my name. Okay, so my name is Manojit Das as I told, and I am doing my PhD under Professor Raghavan B. Sunoj in computational chemistry. So I am one of the TAs in this course, and NPTEL has arranged this interactive session to discuss questions or doubts which you may have, and also discuss some questions within the topic relevant with this course. Okay. So I will be taking these classes every Sunday from 7 to 8 p.m. If you have any doubt, just let me know. I will try to solve those, and if I don't know it immediately, I will try to solve those in the later lectures. Okay. So that's the overall idea of these interactive sessions. So what I am going to talk in this lecture is the very basic fundamental chemistry which is introduced by ma'am in the early lectures. Okay. So the fundamental concept like acidity, basicity, hyperconjugation, aromaticity, and then stability of carbocations, these were the things which were discussed. To discuss this point with some examples, I will present some PPTs. Okay. And that's it. Let's get started with these things. So I will present here my entire screen. Let's get started. Okay. So I'm presenting my slides, right? I have things are visible. Let me go to my PPT, and this is the overall structure. I'm not going to elaborate this once again because I already told. Let me hide this one. Okay. Now this is a simple question related to carbocation stability, and I'm going to discuss it. So since there is no one within this first class, so it's basically I am going to talk only, and if you have any doubts and question, let me know. So I forgot to mention one point that all these lectures will be on available in YouTube, so you can visit the channel and get it anytime. Let's come back to our point. So we had this question like when the alkene 3,3 dimethyl 1 butene, sorry, it is written butane, it will be butene, is treated with hydrogen iodide. So we can see that A, which is 3,3 dimethyl 1 butene, is treated with hydrogen iodide. There is obtained a mixture of products which is written like B, C and D. So overall this question is related to carbocation, how that we are going to discuss, and then the question is which is the major product, and if it is the major product, why it is the major product. It's a pretty basic simple question, and I will show that how these three products can be formed and which is the major product and what is the reason of it. So to do that, I will get out from this, and I have to go to do something here, like let's present in a whiteboard. I will be writing and drawing, which is pretty cool. Okay, so you can see this interesting whiteboard. We like whiteboard rather than blackboard. So remember, I have, let's take this colorful one. So I have, sorry, this is not good. This simple one is better. So I have this alkene system, right? And then we have an acid, hydrogen iodide, H, which is the source of H plus, and then I minus. We can think it of like this. So what will happen is this alkene can attack this H plus, thus it can form two carbocation. So if I name it properly, like this is the first atom number 1, carbon atom, and then 2, then there is 3, and there is 4. Simple. Overall this will give us two carbocation depending on which carbon atom get attached to this hydrogen one, right? So I will draw the first one here. Let's do it. So this one I am attaching hydrogen here. So overall the plus charge is assigned here, and then there is a chance like this let's say the hydrogen is here, sorry, and then the plus charge is here. So this can give, and then the corresponding nucleophilic attack, this I minus can attack at this position, this carbocation, and also it can attack this positive charge. So it will give us, sorry, so it will give us two product, right? What will happen is that we will get from this one corresponding to this one, let me change the color, if I do this, so sorry, this one, so there will be hydrogen here and there will be iodine here. So this is the one product which is shown in the question, you remember? And also we can get from this also, there is a hydrogen here and the iodine will be attaching here. Just a second. Right, and there is a hydrogen here. Now what happened is, then what is the last product which we mentioned in this class, sorry, in this question? So we explained this B and then C, right? And if we compare the stability of between these two, we say this is a secondary and this is a primary. So this will be in a greater extent compared to this one. This is, we can consider as a minor. What about the last product? How it forms? So what if we see that's a 2 degree and it's a 1 degree, but what happens is that there is a chance of migration of a methyl group Y to get a more stable carbocation, which I am going to show here right now. So what happens is that if you imagine any of the methyl group migrates and come to here, so let me get back to here. So what will happen is that this red color you follow just with me. So there is a hydrogen, okay, don't worry about it. So it will be like this. So this methyl group has migrated here. So rather than showing the hydrogen here, I don't want to show the hydrogen here. You just remember that's the methyl group, right? Because the hydrogen attached there. So initially this secondary carbocation is transforming into a, you see it becomes 3 degree tertiary carbocation, right? 3 degree carbocation, which is more stable compared to this one. So initially we showed how the two products are formed, but rather than also we have some chance possibility to get a more stable carbocation, which is shown here. And we know the stability order of simple carbocations like 3 degree, 2 degree, 1 degree, right? So what happens, then the nucleophile can attack in this position to give us the last product which is shown in the question. So like this, and I can have iodine here. So this is the major products. So overall, if I assign it here, for example here, one second. So what we see is that B is coming from a secondary carbocation generation, C is coming from a 1 degree carbocation generation, and D is coming from this carbocation which was there initially for B. So there is a methyl migration to form a more stable 3 degree carbocation, and then the corresponding nucleophilic attack to give us the product D. So how these three forms actually. Now D is the major product because it comes from the 3 degree stable carbocation, and then the order will be B and then the C. Okay. So this was the one question related to carbocation. Another question related to carbocation can be, think of it in aromatic electrophilic substitution reaction. Well, this is one of the important class of reaction utilized in different areas, drug and other things, and it is very well known also. So we have a substituted benzene here, and in the upper 3 structure, if you see, imagine there is a incoming group Y is getting attached at the para position, thereby there is a generation of carbocation. Now this carbocation we will compare with the corresponding carbocation in which the incoming group Y is in the meta position. So imagine this question that the upper 3 carbocation stability we are comparing with the lower 3 one, class A, class B kind of thing. Now what happens is that in the upper classes you see that nitrogen's lone pairs is directly in conjugation with the positive charge. So imagine this nitrogen's lone pair, follow my cursor, it comes here and then the pi bonds come here and it directly stabilizes the positive charge. Overall we see that every structure, like NH2 group here, and then stabilizes, and we get the third structure, right? So overall, this directly stabilizes the plus charge. So this is quite stable. Now compare with this one, whereas here the NH2 lone pairs is not directly stabilizing the positive charge. Thus, we can see that the carbocation stability is one of the fundamental factor which dictates the direction. Where the incoming group will attach, whether it is ortho or meta or para. So, what in the upper class we see the carbocations are more stable compared to the meta attack here. Similarly, you can do also for the ortho attack, and you will see similar situation with similar situation with this para kind of thing. Okay. Thus, we say that this NH2 substitution in benzene ring will direct the incoming nucleophile, aromatic electrophilic substitution at the ortho para position or the meta position. Okay, that's it. So overall, these two questions I have discussed from the carbocation stability, and then come to the next what you see. So we have seen there is a question of basicity. So this is one of the important factor. Now, how do you define a base? A base can be any atom or anything, any substance which can give its lone pair. Like here, oxygen and nitrogen are having lone pair, and we know oxygen is more electronegative and nitrogen is electronegative. So we can think it as this nitrogen's lone pair will be given to some vacant space or any atom or anything. So thus we see that these two are having lone pairs available. Now the question is which one is more basic. The difference between these two A and B is just simple methyl and benzene. This is the difference there, right? Now we'll discuss this question. Let's draw here, and then we can come point. Let's clear the thing. So let's take the red one also, no problem. This carbonyl group, and then NH2 I have, and similarly I have the benzene, keto, and then NH2, right? Now see that NH2 groups and this nitrogen's lone pair, let me draw it in big, is conjugated with this carbonyl system. Thus it is less available compared to a primary amine, right? So it will be of course less basic. Now compared to this methyl group, which is an electron releasing group, this benzene, here the pi electron of the benzene ring is directly conjugated with the carbonyl system, which makes this carbonyl group is the carbonyl group is receiving less amount of lone electron from the amino group. In another way, we can say that the nitrogen's lone pair in this benzamide is more available to give for giving purpose, is more available compared to this acetamide. Okay, so that's why this one, that the B compound, is more basic compared to A. I hope it's pretty simple question, right? So overall this order is like this. Similarly, so thus we can explain the basicity of these two simple compound. Let's go to some another question like this one, acidity. Here it is asked that which one is the most acidic, like 1, 2, 3, 4. The compounds are simple benzoic acid, orthobenzoic acid, and then metabenzoic acid, and then parabenzoic acid. This question immediately looks very simple. We may think it like orthopara are electron donating group, thus it will lower the acidity, meaning that the equilibrium between acid and then the, for example, benzoic acid and the benzoate ion and then H plus. Okay, so this is a little tricky one. I will discuss it here. Let's come to our friendly whiteboard and then clear frame. So what we know is that let's come to this one. First we will compare this para substituted and meta substituted. So we have COO to H, okay, and the corresponding meta one, CO to H. Now it will form the anion, like I am not drawing the full form here, COO minus, and then there will be H plus. So any group which stabilizes the benzoate anion, I mean this one, let's draw it, otherwise it may disturb. So any group, any substituent which will stabilize this benzoate anion, which it will favor the equilibrium, right? Whereas any group that destabilizes the benzoate anion here will reduce the acidity. Now the methyl group, here is the inductive effect, electron releasing, in both cases are there, this is same, but in methyl group the hyperconjugative effect, like this here in para position, destabilizes the benzoate anion much more compared to this meta substitution, because these hydrogens are not directly involved in this hyperconjugative structure, right? So overall, if I compare these two things, the para is the least acidic. So we can say, if I say A, B, C, D naming, so D is the least acidic, or 4. I think I have shown it as the 4. So rather than writing D, I can write it as a 4 to be better. So 4 is the least acidic because of this methyl group. So both inductive effect and then hyperconjugative effect. Now this meta, so this is 3. Now what about the first two one? So we have a simple benzoic acid, I mean there is no substitution, and then ortho substituted benzoic acid with a methyl group. Now what happens is, there you can think it of like a methyl is electron donating group, so it will have a lower acidity compared to the non-substituted one, but this is actually not the case, rather than it is the reverse. So we had this as a 1, I think, and this as a 2. Let me check it out further. Yes, I am right about it. So what happens is that this methyl group and this carboxylic acid group, these are in ortho, very close, and the steric interaction between these two groups makes the COOH group not in plane with the benzene ring. Thus what happens, this pi electron which is in conjugation in here is not conjugation with here. So overall it increases the acidity of this ortho substituted benzoic acid more compared to the here, because in the benzoate anion of this first one is still there is a benzene ring can interact with the carboxylic, that is destabilize the benzoate anion, whereas this, since this is not in full conjugation, so it stabilizes more compared to this one. So thus 2 is more acidic compared to the 1, and we can compare also between 1 and 3. This there is a inductive effect of this methyl group which makes it less acidic compared to 1. So overall this answer is like this. So this is a pretty tricky question, not, I mean, simple, not inductive effect, so please be careful with it. Okay, that's it with this question. Now this is an there are some couple of questions within this slide. So point is symmetry. Our objective is to find the proper axis of symmetry. These are pretty simple molecules. You can readily visualize in different platforms. So I will share one of those, and we'll see these are, one can easily visualize the axis of symmetry. Well, what is the proper axis of symmetry? An operation which involves rotation, and after the operation we get the indistinguishable structure. So a particular operation which will operate on that molecule, and you will get an indistinguishable structure from with respect to the initial one. Okay, so if our eyes are blind kind of thing, we cannot distinguish, okay, I have done something on that molecule, some operation has been done on that. Okay, so I have pretty cool some web platform to check these things, so I will share with you just a second. And this is like I have just, I don't remember where. Okay, so auto, I don't remember that. So let me just a second, give me. I think I have, there it is. So what I have is that I can this website symmetry@orderb. Okay, here you can visualize some cool molecules and their symmetry properties. For example, C2B water is there, and here it is. You see here the 3D structure of water. I think you have earlier visualized this one also. So let's in the right side you see there are point group classes, and I will operate C2 operation here. So let's operate this. See, so there is a C2 along this line passing through the oxygen atom. I can click here, and you see it is written here, C2 is coming just up the oxygen. So now it is much more visual. So if we rotate it, we can see there is a C2 proper axis of symmetry. You see this dot line at the below, and then up C2 is written, so passing through the oxygen. Similarly, what we have is this CHCl3 and then ammonia also. Well, we can see the ammonia quite easily here, which is in this group, pyramidal C and B group, and there you go, ammonia. See, it's nice looking and good looking. So there are 3 hydrogens are there. So at the right side we see that there are C3 rotations are possible here, and there are 2 written and 1 is inverse. So we are not don't have any interest on that right now. So let's see the C3 rotation, how it looks like. See, nice, right? Similarly, you can thus see in ammonia there is lone pair, whereas in this CHCl3 it's just a hydrogen. Overall, there are some similarity between these 2 things, right? So this also have C3. If you just rotate along the CH bond, you will have C3 rotate, proper axis of symmetry. Interestingly, this one, that is tertiary carbocation, also has the C3 proper axis of symmetry. Here I don't have the directly tertiary carbocation right there, but I have here BH3. So let's just wait for a second. Dihedral, cyclic. Just a second. Triplet ammonia cyclohexane. Nitrogen. Diborane, naphthalene. There I go. It took so time. It is So see, it's a very similar to a planar carbocation structure. Imagine that it's a C and then all are C atom. Okay. So at the right side you see there are C3 rotations are available, and then again there are 2 of them based on your direction. So if I rotate it like this, see, it is also having C3, but this C3 is different from the, in terms of visualization, we see it is same. It's just a planar structure is also having C3, and then pyramidal structures are also having a C3 rotation, right? Ammonia also had this C3 rotation. And then what we have is then acetylene kind of molecule, and then this anti to the disubstituted chloro, and then naphthalene. So we can look at these things. Naphthalene is close here, so it's a tricky one little bit. So we can see that one can pass like a C2 rotation from along this bond, right? So if I imagine this CC bond is a C2 axis. So for example, if I rotate it, not this one, I am talking about this one. See, this one I was talking about, this is a C2 rotation. Similarly, one can have this rotation also. So this axis is passing through all this CC bond, this CC, this and this. So imagine an axis passing through, imagine axis passing through all these bonds, in between the bonds. So like this, and also you have a Z along Z axis. See, it's perpendicular to the plane of the molecule. So overall there are 3 C2 proper axis of symmetry. And I can also show the other one, like here it belongs to the first class, here not acetylene. We can see it is not same as I am shown in the presentation, but it is having the same. So a C infinity rotation, which we cannot show because any degree of rotation you do, we get the indistinguishable form from the initial one. So it has a C infinity passing through all the atoms involved here, like H, C, C, H. So this has a C infinity, right? And then this dichloro is also having a C2, which passing perpendicular to this carbon-carbon plane, right? So you just rotate it along this axis, you will get the same orientation. Basically what you see is that mostly here it is C2 and C3 are there. So this was the question from the symmetry part. Next what we have is the hyperconjugation. The question is pretty simple here. We can see it says how many hyperconjugative structures are possible. Let's draw them all. So it's a pretty simple question, and all we need to find out is how many hydrogens are there at alpha position, right? So let's get back to our this one clear frame, and here we are. We need to draw some small molecule like this one. It's a cyclohexane, there is a methyl and then ethyl group, and there is a carbocation, right? So this is a question related, can be from stability of carbocation again. So we need to assign the hydrogens here. So there are like CH3 here, and then there is CH2 actually, and there is the one hydrogen is also here, carbon is tetravalent, right? So what we can see, that imagine I can this one makes a hyperconjugative structure like this one. So what we will have, yes, I am correct about it. So this is the class and then H plus, right? This is one of the structure, this alpha. So this one is alpha position, this one is alpha position, this one is alpha position. Overall, let's just count the hydrogen, number of hydrogen, that is 1, 3, 4, 5, 6. So I can draw 6 structure like this. So number of hyperconjugative structures are 6. I hope you can draw all them by your own. So overall, these were the questions which I am trying to discuss here. So we started with carbocation stability with 2 different questions. How can different products formation can be analyzed? What is the major product? How the carbocation stability dictates the ratio of the products, and then how the carbocation stability dictates the direction. I mean ortho, meta, or para directing group. And then we talked about basicity, how an atom substitution can affect the basicity order, and then we talked about a tricky question on acidity of substituted benzoic acid, how the both inductive effect and then ortho effect, where the methyl group and carboxylic acid group is in static interaction, thus they destabilize, not destabilize, but rather the interaction between the planar benzene ring and the COOH is lost somewhat. And then we talked about also some symmetry operations, and like C2 and C3 we show some wave platform where you can really visualize the axis of symmetry, how they are passing, and what make them on operation on that molecule gives us the indistinguishable structure from the initial one. And then we talked about also hyperconjugation and how do we get the hyperconjugated structures, right? So I hope this gives you a much wider view of the basic chemistry, and I hope you get some helps from this, and I will see you in the next class onwards, and you will join, and I'm eager, or I'm curious to know to you all. Thank you so much, and I will stop this here. Thank you.